G'day Ian, welcome back to Mathematics 302. Hope you're having a good morning or a good evening, as the case may be. This is lecture 12. We are working through practice questions for the final assessment. So in this one, we've got open, clopin, and closed, De Morgan's law, echelon form, equivalence relation, partition, topological space, and a proof by induction. Okay, let's get into it. Question 1. Describe the following sets. We've got minus z to z, where z is an element of C, 10 to 100, where r is an element of the reals, minus 100 to 100, where q is an element of the rationals. So answers, which is pretty much what I've just said. We've got an open set in the complex from minus z to z, and you can reword this backwards, forwards if you're wanting to say things exact. It's a clopin set in the reals from 10 to 100, closed at 10, open at 100, and a clopin set in rationals from minus 100 to 100, closed at minus 100, and open at 100. So there we go. That's a pretty easy way to describe the following sets. Question 2. Prove De Morgan's law. First law holds where U equals A, B, C, D, E, F, G, H, A equals ACE, and B equals EFH. Now, you've probably seen this question before because I know you've done it. So this is just an example because I didn't want to create a whole new question. The question in the assessment's a little different, but very similar. De Morgan's first law, the complement of the union of two sets is the intersection of their complements. So A union B complement equals A complement intersection B complement. So this is the one we're going to prove. De Morgan's second law, the complement of the intersection of two sets is the union of their complements. So it's effectively the reverse of this. A intersection B complement equals A complement union B complement. I think in the instance where I give this in the test, I think to give you this is not such a bad idea. So you're not thinking, oh, is it the other way or is it one way or the other way around? I think giving you De Morgan's first and second law is appropriate. So answer, left-hand side, and that's what you literally do. You just go through, show the left-hand side, show the right-hand side, and then say they're equal. So left-hand side, A union B, so we're doing this. A union B is ACE union with EFH. So then you get ACEFH because, mention the E twice. Hence, A union B complement is just whatever's left, which is BDG. So now we've got A union B complement. That's this bit here. We've got the left-hand side. So now let's do the right-hand side. So the right-hand side, we're looking at this. Well, A is ACE. So A complement is BDFGH. And then again, B is EFH. So B complement is ABCDG. So now we want to do A complement intersection B complement, which is these two. We're intersecting these two. So what is the intersection? And it equals BDG. Look at that. It's exactly the same. So the left-hand side equals the right-hand side. Therefore, we've proved it. We've proved De Morgan's first law. Okay. It's pretty straightforward, pretty logical. If I give you those, you should knock it out of the park. Question 3. Write an equivalence in full echelon form for 2068, 1326, 2734. And again, you've seen this question before. I've left out the line in all of these, just simply for speed and getting it done. Okay, so we've got 206. I'm going to do line 3, subtract line 1. So line 3, subtract line 1, I'm going to get a 0. 7, obviously taking away 0, minus 3, taking away the 6 from the 3, I get minus 3, and taking away the 8 from the 4 up here, I get minus 4. The idea is you want this 1, 2, and 7 just to be zeros. Then you've got it in simple echelon form, and full echelon form is where you've got just the center row and nothing else. So here I've done line 1 divided by 2. So I've just halved line 1. So just divide by 2, divide by 2, divide by 2. So now I've got a 1, a 0, and a 3, and a 4. So I've got another 0 in there, but that's now a 1, which is easier to work with. Now I'm going to do line 2 subtract line 1. So I'm just going to go 1 take away 1 is 0. 3 take away 0 is obviously still 3. 2 take away 3 is -1. 6 take away 4 is 2. So we're getting pretty close here to what we want. And now I'm going to do line 3 times 3 minus line 2 times 7. So line 3 times 3, so that makes this 21, and it makes this 21. So that's going to subtract. And so line 3 times 3 here is -9, minus line 2 times 7. So this is going to be plus 7. So I'm going to get 9, sorry, -9 plus 7 is -2. And same here, line 3 times 3. So I'm going to get -12 minus 2 times 7, which is 14. So 12, 14 gives us -26. So effectively here, I've got echelon form. I put a little smiley face to say, yay, we've got our 3 zeros. Happy place. I should have the lines down there, but I've left them out. Keep on going and we'll get it to full echelon form. So we'll just start wiping out other things. So just dividing the bottom one by 2 and then deleting, so adding line 2 to 3. I haven't written what I'm doing here. I've just done it fairly quickly. So just adding line 3 to line 2. So that plus that's still 3. That plus that is 0. That plus that is 15. So now I've got a 0 there. So I've only got 1 3 to get rid of. So I'm going to do this line, subtract 3 of this line. So that gets us, whoops, did I do that? Oh, sorry, whoops. I divided the middle line by 3. So that divided by 3 is 1, and that divided by 3 is 5. So now I'm going to do the final step, which is this line subtracting 3 lots of this line, and that gives us the 0 minus 35. There's full echelon form, and that gives us our answer. Z is 13, Y is 5, and X is -35. So there we go. Okay, it's a pretty straightforward test, pretty straightforward process, and again, you should knock it out of the park. Just make sure you're doing it step by step. You want to check things when you get back here. Really easy check is just grab one of the lines at the start and put the numbers in. So just go here, 2 times -35 plus 0 times y plus 13 times 6, and make sure it equals 8. And if that works, then you know you've got it correct. You don't have to check every single line. I probably wouldn't check the one with 0. I'd probably actually check one which hadn't got a 0, so maybe check the bottom line, because then you're using each of the terms. Anyway, that's just a tip. Question 4. Write an equivalence relation for y equals x squared plus 2x plus 1. Well, this is really a straightforward, knock it out of the park one. What is this? Well, that is a perfect square, obviously. So any other perfect square will satisfy that in R2. So we'll just make one up. X squared plus 4x plus 4. There we go. Done. So pretty easy. You should be able to figure that one out pretty easily. Okay, identify those which are valid partitions of 1, 2, 3, 4. So here we go. We've got 1, 2, 3, 4. Oh, sorry, 1, 2, and 3, 4. 1, 2, 2, 3, and 3, 4. The empty set, 1, 2, and 3, 4. 1, 2, 3, and 4. The first question which should run through your brain are, what are those partition rules again? I'm glad you asked. Here we go. Rules for partition. Union of the subsets must be the original set. So union of the subsets, so union of these two, must be the original set. Tick. Subsets must be non-empty. Well, that's going to wipe out C, isn't it? You can't have the empty set in a partition. Subsets must be mutually disjoint. Well, that's going to wipe out B, because here you've got 2 and 2. They're not disjoint. The other ones, A is correct, and D is correct. So our answer, A and D are correct. B contains overlapping entries in multiple blocks, so that's out. And C contains the empty set. So yeah, just pay attention here. Partitions, we don't want the empty set. For the next question, when we get to question 6, we do want the empty set. So just pay attention to the question of what question you get in the assessment. So valid partitions. Union must be the original. Subsets non-empty. Mutually disjoint. You don't want anything overlapping for a partition. Question 6. Identify those which are not topological spaces of 1, 2, 3. Now, it looks very similar in the layout here. You've got these, so pay attention to the question being asked. Topological spaces. And you'll notice here every single one has got the empty set, so I'm making it easy for you. In the assessment, some of them might not have the empty set. So topological spaces, again, what are our rules? Our rules are must contain the empty set. Look at that. Must contain all unions, must contain all intersections. So we want to find the ones that are not topological spaces. So this has got the empty set in 1, 2, 3. Well, it does contain the empty set. All unions, well, 1, 2, 3, union with 1, 2, 3 is still 1, 2, 3. All intersection, well, that's itself. So this is the simplest topological space. 1, 2, 3, and the empty set. So that's obviously valid. Here, if we get 1, union with this is going to be 1, 2, 3. Intersection with this is just going to be 1, so that's going to be valid. Here, let's look at this. We've got 1, 1, 2, and 2. If we union 1 and 2, we get 1, 2. If we intersect with anything, we intersect these two, we're going to get 1. And if we intersect these two, we're going to get 2. So this looks valid as well. Here, we're missing a union. 1, 2, you should have 1, 2. So this one's valid, this one isn't. And here, we're missing an intersection. We intersect these two, we should just get a 2. So our answers A, B, and C are valid. D is missing the union of 1 and 2. And E is missing the intersection of 1, 2, and 2, 3. Okay, hopefully pretty straightforward. Last question, and a bit of a long one here. Prove by induction that the following sequence has a limit, and then find the limit. Now, you should have seen a very similar question to this before. So, answer. And to do any induction, really good plan, write out the first few terms so you can see what's happening, especially if you want a limit, you want to see what's happening. There's 1, there's 2, the next one's going to be 7 on 3. The next one's going to be 22 on 9. So you can see this pattern here of 1, 2, and this is 2 and 1/3, and this is 2 and 4/9. So it's gradually increasing, but increasing at a slower rate. So it looks like the limit, you'd probably guess a limit of, say, 3. That will be limited by 3. There might be a lesser limit because we've got to find it. So first of all, prove it's monotonic increasing because this is obviously increasing. So we want to prove that this is bigger than this. So the second term is bigger than the first term, or similar. Depends on how you word that in your head. So A1 is less than AN plus 1 because we can see 1 is less than 2 is true. So that's obviously, yay, big tick for the first step. Second step, assume true for AK plus 1 is less than AK plus 2, or AK plus 2 is bigger than AK plus 1, i.e. AK plus 5/3 is less than AK plus 1 plus 5/3 is true, and I put a red star on that. When you're doing induction, typically you will use the assumption again. You may or may not, depends on how the induction goes. You may get through it and you may go, oh, I didn't actually need it. But you're likely to need it, so you put a star on it to say, I'm going to refer to it again. Show it's true for AK plus 2 less than AK plus 3, i.e. this is less than this. So let's do that. So now we're going to write it out. I've actually written less than or equal to there, don't need to, because it's got to be increasing. So here what we're going to do is we're just going to cut out things. So we've got plus 5, so let's just expand that to plus 5 on 3, plus 5 on 3, and then we're going to cancel these out because they're common. So they're gone. So now you've got divide by 3, divide by 3. Well, you can cancel that out as well. So now you're going to have AK plus 1 is less than AK plus 2. And that's our original assumption, isn't it? So we've got our assumption here. So from our assumption, I am using it. So it's true since that's our initial assumption. So we've now proved it's monotonic increasing. Next thing we need to prove is it's bounded by induction. And again, I've written out the terms there so we can see what they are. This time I've written them out as 2 1/3, 2 4/9. We're going to show it's bounded, and again, use induction. So let's put the bound at 3. So 3 looks good. If it fails, well, do 4. Okay, so A1 equals 1, and that's less than 3. Tick, that's the first term is valid. Assume true for AK plus 1. But here there's a little thing you can do to speed it up. You can go through the steps and do those if you want. But here we can just substitute in the limit. We think the limit's 3. So let's just do that. We're just going to put, instead of going through the steps, we're just going to put in what we think the limit is. So if we put in 3, 3 plus 5 is over 3, is 8 over 3, which is 2 2/3, and that is less than 3, and that's true. So if we're thinking the limit, the maximum limit is 3, and we put the limit in, and that is less than the limit, well, we've done it, haven't we? We've shown it's bounded. So that's a neat little trick you can use when you're going through something like this. You can say, well, I'm going to say it's less than 3. Hang on, what if I put in the limit and put it in, and it's still less than the limit? Well, done. Fantastic. So, if you're putting in a limit which is bigger than it and it doesn't work, you're like, that didn't work. But in this case, you can have this neat little trick. So therefore, it's going to be true for all k, because if it's true for the limit, it's true for everything. Now we want to find the limit, and that's a fairly easy process given this thing. We're going to use the limit again. We're going to substitute the limit and just use algebra. So we're going to say we've got a limit, whatever that is, equals the limit plus 5 over 3, and we're just going to use algebra. So multiply by 3, 3L equals L plus 5, take off L, 2L equals 5, therefore the limit is 5 on 2. And that's it, done. Okay, it's a pretty straightforward sort of process when you've got something like this, and hopefully it'll be that straightforward in the test. That's all for this one. Okay, I'll see you in part D. I've got a list of the contents which are now posted. So God bless you, stay safe, and I'll see you in part D. Okay, bye.